Welcome to 2.7. What you see in front of you is the last page of your lecture notes, and it's a chart that tells you how to go from any one coordinate system to the other using 3 equations. And we're going to be using this chart today. Now the volume elements are down here. We'll be using those next time in order to integrate. Now I'll give you this chart and the volume elements on tests, so don't worry about memorizing those formulas. Okay, let's jump up here and start with cylindrical coordinates, which are simply polar coordinates in the plane, and then to get the third dimension, we take z from the rectangular coordinate system. So it's a combo of polar and rectangular. And so let's just do some conversions here. Let's plot this point and then find its rectangular coordinates. I'm going to do the plotting first. Theta equals 0 is the positive x-axis. Theta equals pi over 2 is the positive y-axis. So 2 pi over 3 is probably about here. And it's 2 units out because r is 2. And then z is 1, so you go up 1 unit. So there's our point. Now let's find its coordinates. These formulas here are straight from the chart on the last page. X is r cos theta, so that's going to be 2 cosine of 2 pi over 3, which is negative 1/2. That gives us negative 1. Y is r sine theta, so 2 times root 3 over 2 is root 3. Sorry, up here, that's a negative 1. And then z is z, so x, y, z is negative 1, root 3, 1. Since we now have 3 coordinate systems, I like to label every point so you know which coordinate system I'm talking about. Okay, now let's go in the other direction. We want cylindrical coordinates for this point here, and we want r and theta to be positive. So let's start with r. R is the square root of x squared plus y squared. So that's the square root of 3 squared plus negative 3 squared, which is square root of 18, which is 3 root 2. Tangent theta is y over x. So that's negative 3 over 3, which is negative 1. So there's 2 angles we could use here for tangent theta equal negative 1. So what we have to do is figure out what quadrant in the xy plane we're in. So I'm going to plot this point, 3, negative 3. That's down in quadrant 4. So I want to use theta equal to 7 pi over 4. The other option would be up here, theta equal 3 pi over 4, but our point, the xy coordinates are in quadrant 4, not in quadrant 2. All right, and z is z, which is negative 7. So r theta z is 3 root 2, 7 pi over 4, negative 7. Okay, one more. Maybe you should pause the video and do this one yourself. Okay, we're back. R is the square root of 5 squared in this case, which is 5. Tangent theta is 5 over 0, which is undefined. So theta is either going to be pi over 2 or 3 pi over 2. Which is it? Well, let's take a look at x and y. X is 0, y is 5. So we're up there on the positive y-axis. So we want theta equals pi over 2. And z is z, which is 2. So r theta z is 5, pi over 2, 2. All right, let's look at some surfaces in cylindrical coordinates. These are the typical surfaces we'll be integrating with: cones, cylinders, elliptical paraboloids, and half planes. Half plane because r is positive. And over on the right here, I've given you an example of each one, like r equals z, r equals 5, r equals root z, and showed you how to get to the rectangular equation from the cylindrical equation. So let's just look at r equal 5 here for a second. Why is that a cylinder? If we look just in the xy plane, r equal 5 is a circle of radius 5, but z is free, and so that's what gives us the 3D cylinder. All right, so let's look at a typical problem. Convert this equation to cylindrical coordinates and sketch. All right, so we can replace the x squared plus y squared with an r squared, and we can replace the y with r sine theta. So this is 6 r sine theta. We want to solve for r, so divide both sides by r, which is fairly safe with polar coordinates. Usually you don't lose any solutions. So r is 6 sine theta. Well, we know in the polar coordinate system, that's a circle of diameter 6, and it lies on top of the x-axis like that. So in 3D, let's redraw that circle. That would be here. As you know, I'm not the best artist. And there's our cylinder there. All right, and now we get to the spherical coordinates, which is a little more interesting. We define the coordinates for the point to be rho, theta, phi. Theta is the exact same theta from cylindrical. Rho is the distance of the point from the origin. So the distance of this line right here. And phi is probably the most interesting coordinate. That's the angle from the positive z-axis to the line OP. And so I think showing you a little app is going to help you here. In this app, they're calling rho R, but otherwise phi and theta are the same. Varying rho is going to change our distance from the origin. So setting rho fixed is going to define a sphere. Theta is going to swing us around the positive z-axis. And let's take a look at phi. Phi only goes from 0 to pi. That's it. And if we fix phi, we're going to get a cone. So you might want to play around with some of those apps for spherical coordinates to get a feel for what they're doing. Okay, so let's go back here and do some more conversions. Now we're going to convert a rectangular to a spherical. Rho is square root x squared plus y squared plus z squared. And again, these three equations are coming from the last page. So 0 squared plus 2 root 3 squared plus negative 2 squared is the square root of 12 plus 4, which is square root of 16, which is 4. So our point is 4 units from the origin. Tangent theta is y over x, which is 2 root 3 over 0, which is undefined. So that means theta is going to be pi over 2 or 3 pi over 2. So again, we need to see what's going on in the xy plane. X is 0, y is positive, so theta is pi over 2. Phi is cosine inverse of z over rho. That's why you have to find rho before you can find phi. So this is cosine inverse of z, negative 2, over rho, which is 4. So cosine inverse of negative 1/2, which is 2 pi over 3. So our spherical coordinates, I'll put up here, equal rho theta phi, equal 4 pi over 2, 2 pi over 3. Now, phi equals 0 is the positive z-axis. If you're in the xy plane, then phi is pi over 2. And if you're down here on the negative z-axis, phi is pi. So with phi being 2 pi over 3, we know we're down below the xy plane. Okay, now let's go from rectangular to cylindrical. R is the square root of x squared plus y squared. So that's going to be the square root of 2 root 3 squared, which is 2 root 3. Tangent theta is y over x. So 0 over 2 root 3 is 0. So that means theta is going to be 0 or pi. So which is it? Go to the xy plane. X is positive, y is 0. So we want theta equals 0. And then z is z, which is negative 2. So our coordinates are 2 root 3, 0, negative 2. I encourage you at this point just to pause the video and compare the three coordinates that we have for this point. So we have rectangular, spherical, and cylindrical for the same point. Okay, and this last one I just did out. When you go from spherical to rectangular, there are no choices to make. You use these three equations and you get the coordinates that I have listed there. But I just wanted to show you this one in terms of the picture over to the right here. We know phi is 2. So since phi is 2, we know we're somewhere on this sphere, rho equals 2. Then when we set theta, theta is pi over 4. So we know we're somewhere on this half plane, theta equals pi over 4. And finally, phi equals pi over 3. That's defining this cone here. So if we have to be on all three surfaces at once, we're right here at this point in the first octant. Okay, so let's look at some surfaces, but now in spherical coordinates. Cones are going to be, as I stated before, determined by setting phi equal to a fixed number. So for example, if phi is pi over 4, you're just getting our friendly rectangular cone. Spheres are defined by setting rho equal to a constant, and horizontal planes will be A secant phi, and I've got a description of that over here. Okay, so finally, let's look at this example here. Convert to spherical equations and determine the value of phi where the surfaces meet. So the important relationships we need for this problem are rho and z in terms of rho and phi. So when we write z equal 1 in spherical coordinates, come over here, put 1 in for z, and set that equal to rho cosine phi. Now solve for rho. Rho is 1 over cosine phi, which is secant phi. So that is our plane, secant phi. Now our sphere, this is a sphere of radius 2, so that's just setting rho equal to 2. So those are the two surfaces in spherical coordinates. Let's determine where they meet. We're going to set rho equal to rho, So we get secant phi equals 2. Let's change that over to a cosine problem. Let's take the reciprocal of both sides of that equation. 1 over secant phi is cosine phi, and 1 over 2 is a half. So cosine phi is a half, so we know that phi is pi over 3. Okay, I'm going to do something extra. Suppose we wanted to, in the next section, we're going to want to integrate, for example, over this top cap. So let's find some inequalities that determine what that top cap of the sphere is. And I mean everything on the sphere above that plane. And so if I imagine a ray emanating from the origin, it's going to hit that top cap. So these are the limits on rho. It's going to hit that top cap when rho hits secant phi, and it's going to leave that top cap when rho is 2. What are the limits on phi? Well, when phi is 0, we're inside of the region. So phi is going to start at 0, and it's going to go, those rays are going to stay in the cap, bam, until you hit the angle pi over 3. And finally, the easiest is theta. We want the whole cap all the way around, so theta is going to go from 0 to 2 pi. So if we wanted to integrate over that region in spherical coordinates, those would be the limits that we would use, and we'll do that next time. Okay, and that's the end of this section.